Folks, here we're asked to evaluate a line integral where C is a given line segment and we're sitting inside of a vector field. We're told that this vector field is conservative. There's a long way to do this problem, but I'm not going to jump into that. I'm going to work the problem the quickest way I know how, and then at the end of the video I'll show you how you could go about solving this the long way. The key issue here is that we can use the fundamental theorem of line integrals because we know that we're in a conservative vector field. The problem is we don't know the potential function phi that generated this vector field. So we'll have to identify that. Let's jump into it. So we're told that f is conservative, which means that f is equal to some gradient of some potential function phi. So we need to figure out what phi is. In this problem, I can actually just identify phi by inspection. If you like, at the end of the video, you can observe as I calculate phi using the techniques used in class. But I'm just going to go ahead and figure out that phi of xy is equal to e to the xy plus the sine of y. And I did that from inspection, but I'm going to check my work just in case. Remember, when I say that f is equal to grad phi, what I mean is that f is equal to partial phi partial x, comma, partial phi partial y. And if I take partial phi partial x, if I take the derivative of this with respect to x, then I would just simply get y e to the xy. And if I take the partial derivative of this with respect to y, I would get x e to the xy plus the cosine of y. And so, sure enough, we found the function phi that generates our potential function. As I said, later in the video, I'll show you a methodical way of calculating that phi of xy, if you like. The next thing we should do is let's just give ourselves a quick visual of the region that we're working with. You actually don't need the picture, but I'm going to go ahead and sketch it anyway. So here is the point P labeled 1, 0, and here is the point Q labeled 0, or point Q at 0, 2. And our path is this directed line segment moving in this direction. Okay. We do need to know the start point and the end point because the order makes a difference there. So when we go to compute the line integral of f dotted with dr, another way to think about that is we're going to be computing the line integral of grad phi dot dr. And this basically boiled down to the fundamental theorem of calculus, which said that we could evaluate this at phi of, well, my endpoint, which we've labeled q, minus phi of my starting point, which we labeled p. That is, that would be phi of 0, 2 minus phi of 1, 0. So all that remains to be done is to evaluate the function phi at these 2 points. So we'll calculate that now. This would be so we end up with an answer of just the sine of 2. That concludes the work for this problem, but I want to go ahead and point out a couple of other things in case you're interested. The first thing is how did we compute, what's another way to find what phi of x was, or phi of xy? So, just as a reminder, we were told that f was this function, this vector valued function, and so we also know that f is equal to phi of x, comma, phi of y. So one way to build phi of xy is to take the antiderivative of phi of x dx, which would be the antiderivative of y e to the xy dx. When I do so, I get e to the xy plus some function c of y. Remember that as far as x is concerned, c of y is a constant, but it may be that it's a function in its own right, and in this case it is. So the next thing to do is to remind ourselves that phi of y needs to be equal to this expression. But we just said that phi was this, and so if we compute phi of y using this formulation underlined in green, we would get x e to the xy plus c prime of y. But if we get it by equating these two expressions, then we have that needs to be equal to x e to the xy plus the cosine of y. Therefore, c prime of y needs to equal the cosine of y, which tells us that c sub y would be the antiderivative of the cosine of y dy, which is equal to the sine of y plus c, and we'll just pick c equal to 0. So putting all that together, that's how we find that our phi of xy is equal to e to the xy plus the sine of y. Some people may say plus c, but I don't need that. So that's how we found, and I did that by inspection without really doing the calculation. That's how we found what our phi of xy was. The last thing I'd like to do is to show how you could have gotten this problem the long way, although I don't think that would be particularly helpful. So another way to do this problem is to go ahead and compute the line integral directly, which I'll do now. When you're computing a line integral, this formulation of it is, well, nice and compact. It's not particularly helpful, and so what we usually do is we give some sort of parameterization of it. So this needs to be some f of t dotted with r prime of t dt, where r is a parameterization of our curve. So we need to write c in terms of some parameterization. And in this case, it's going to be a line. So we need to make sure that when we plug in 0, we get out the point 1, 0. And we plug in time equals 1. We want to get out 0, 2. And we want to do that in a linear fashion. So I think parameterizing this with respect to time, we should have 1 minus t and 2 minus t, or 2t. And this will hold for 0 less than or equal to t less than or equal to 1. And as always, I recommend that you check at least the two endpoints and then confirm that your parameterization in this case is aligned like it's supposed to be. So r of 0, you'll note, is the vector 1, 0, which corresponds to the point 1, 0, so check. And notice that r of 1, if we plug in a 1 for t, we get out the vector 0, 2. So that corresponds to the point 0, 2. So check. So we can now go ahead and write our line integral as the integral from t equals 0 to t equals 2. But then we need to go ahead and parameterize our vector field. So I'm going to take and replace each of the x's in my vector field with 1 minus t, and each of the y's in my vector field with 2t. So this will give me 2t e to the 1 minus t times 2t for the first coordinate of the vector field, comma, the second coordinate would be 1 minus t e to the 1 minus t 2t plus the cosine of 2t. And I'm out of room, so let me scoot that down. That should be, I guess, a closed parentheses. Then close the vector. And then we're going to dot that with r prime of t, which would be to dot this with the vector negative 1, 2 dt. So folks, you could compute this directly. I'm not going to, but I wanted to show you that you could set this up in a straightforward manner. But of course, this problem was geared towards the fact that you would recognize the fundamental theorem of line integrals applies. That way you don't actually have to compute this. If you have any questions about that, let me know.